Okay. Now, one thing that's come up during the last couple lectures is given a vector field f in 3 dimensions, see that f is conservative if we have these 3 conditions. So qz is equal to ry, py is equal to qx, and pz is equal to rx. Right. But another way of looking at it, and I mentioned this last time, that this is the same as saying that this vector of differentiation operators, ddx, ddy, ddz, cross product with p, q, r, which happens to be equal to, so ry minus qz, pz minus rx, and qy minus px. All right, so we have these differences correspond exactly to these equations here. So if this happens to be equal to the 0 vector. So this operation, taking the cross product of differentiation operators with a vector field, turns out to be convenient for this purpose, but it actually is quite useful more broadly than that. So this vector here, cross product of the differentiation operation, ddx, dy, ddz, with a vector field, 3 variables, this is called the curl of f. Okay. All right. Now, it turns out that this has a nice physical interpretation when f happens to represent a velocity field for a fluid. Okay. All right. Okay. So the idea is then curl f is the axis of a direction given by this vector. So keep in mind, cross product is a vector. But curl is the axis around which a fluid is rotating. If it's rotating at all. So that means that if a curl is equal to the 0 vector, means that the fluid is irrotational. So there's no whirlpool, there's no vortex, nothing of that nature. Otherwise, not only does the direction tell us about which axis the fluid is rotating, say in a situation like this, if we have a whirlpool going on here, then the axis, the direction that's orthogonal to this whirlpool, that's curl f. Okay. So if curl f is non-zero, we actually have some spinning going on, then the magnitude of this vector is useful also. It indicates speed of rotation. So if the rotation around this axis is not very fast, we'll have a nice tiny vector here in this direction, but if it's spinning really fast, we'll have a nice long vector. Okay. By the way, one way to learn more about this stuff and how vector calculus operations relate to are used to help model fluids and study fluid mechanics. There's an excellent book on that subject, which I thought was one of the best written math books I've ever seen. And one of the authors is Gerald Marsden, who writes the other vector calculus book we're using in this class. Okay. I have a copy in my office. So this is one operation of the curl that's useful for studying fluids. But even if F does not represent a velocity field, we still have this test that if the curl of a vector field is equal to 0, then we know that that field is conservative. But what else does it mean for a vector field to be conservative? How did we define that in the first place? If big F is a conservative vector field, what does that say about big F? Oh, somebody should remember this. No? Yes.
Is the path independent?
Yes. Oh,
No.
oh, path independent bit? Well, that's important too, but what we care about is the fact that, yeah, big F is a gradient of a function. All right, so what that means is, okay, that if big F is conservative, then curl F is equal to 0, but big F is the gradient of some function little f. So that also is 0. So this leads to one thing that's very important to know about the curl operation. The curl of any gradient is 0. So that's one thing to keep in mind. It's going to come up. Nice topic for the oral exam. Well, either final really. It's going to come up. So just know it. The curl of a gradient is a 0 vector. Okay. All right. Now. All right. So this is one important operation. The cross product of this vector differentiation operators of a vector field. But there's another operation that's quite important as well that involves the dot product. So in this case, the dot product of this differentiation vector with a vector field is called div f, short for divergence. And this, since the dot product of two vectors is a scalar, we have a scalar valued function. So we take derivative p with respect to x plus derivative of q with respect to y plus derivative r with respect to z. So this is the divergence. Now, the divergence has a nice interpretation when big F is a velocity field for a fluid. So, okay. So in this context, the divergence measures the tendency of a fluid to, shocker, diverge from a given point. So the divergence at a point indicates how likely the fluid is to diverge from that point.